So let us solve some more questions from the chapter Convection. Okay. Air flows over a heated plate at a velocity of 50 meter per second. Okay. So the velocity of air flowing over the plate is given. Let me just adjust it. That is 50 meter per second. Okay. V or V infinity. The local skin friction coefficient at a point on a plate is 0.004. The local skin friction coefficient is given. That means we may have to use Reynolds analogy while solving this question. We may have to use, okay? This is how you analyze a question from the data given, and this is how you solve a question, okay? You start reading the question, you start marking down the data, and you start thinking that which are the expressions in which this term can be used. So we may have to use Reynolds analogy in this question. Local skin friction coefficient, that is CFX, is equal to 0.004. Okay. The following properties for air are given. The density is given, viscosity, that is this is dynamic viscosity. Specific heat is in kilojoule per kilogram Kelvin, so that will be 1001 joule per kilogram Kelvin. Okay. The thermal conductivity is given, and see, this is given that you have to use the Reynolds analogy. This is Stanton number, Prandtl number is equal 1 by 3. This should be 2 by 3. This is a printing typing mistake. So it's given that you have to use Reynolds analogy. Okay. So we were correct. Yeah. Okay. So the local heat transfer coefficient is, okay. So simple question it is that local Stanton number into Prandtl number raised to the power 2 by 3 is equal to CFX by 2. Okay. And what is Stanton number? The expression for Stanton number, it is H rho VCP. Okay. And Prandtl number is mu Cp by K. Mu Cp by K raised to the power 2 by 3, which is equal to CFX by 2, that is 0.004 by 2. Okay. Now I have to find the local heat transfer coefficient, this H. Do I know other values? Do I know rho? Rho is 0.88 kilogram per meter cube. Yes. V is 50 meter per second. Cp is 1001 joule per kilogram Kelvin. Do not put that in kilojoules, okay? Mu is yes 2.286 into 10 to the power minus 5 kilogram meter per second, that is Pascal second. Cp, yes. K, thermal conductivity of air is given. Okay. So everything is given to you. You have to directly find H. Okay. So this is the only relation that relates the drag coefficient with the local heat transfer coefficient. Okay. So H is Hx is, this is X, local heat transfer coefficient, Hx at that point. Hx is equal to, the answer is 116.89 watt per meter square. Watt, that is B option. Okay. This is the common data question. So the second question will be based on this data only. The average heat transfer per unit area. Okay, mark the word average. Heat transfer per unit area if the temperature difference is 60 degrees Celsius and the flow is assumed to be laminar. Okay, so for the average heat transfer per unit area, that implies Q bar is equal to H bar A delta T. Now here, do not use local heat transfer coefficient. You have to use average heat transfer coefficient. Okay, and how do you find this average heat transfer coefficient? There is a relation that you must have studied, that H bar is equal to twice of H at X is equal to L. Suppose this is a plate of length L and air or whatever fluid is flowing over it. So the local heat transfer coefficient, the value of the local heat transfer coefficient at X is equal to L is half of the value of the average heat transfer coefficient. Okay, and how do you get this relation? I can explain that to you shortly by using this formula, which is 1 by L 0 to L Hx dx. By integrating all the local heat transfer coefficients over this whole length L, you get average heat transfer coefficient. Okay, and what is this Hx in case of laminar flow? Hx is directly proportional to x raised to the minus 1 by 2. X is the distance from the leading edge. Okay, so replace this proportionality sign with the constant c, which is c x raised to the minus 1 by 2. Now put this term here and integrate it from 0 to L. You will get h bar, and the relation is this: h bar is twice of the local heat transfer coefficient, the value of the local heat transfer coefficient at x is equal to L. Okay, you must have done this, but I have told you this in a shorter way. Okay, so h bar is twice of h, the local heat transfer coefficient at length L, which we have found out, and whose value was this 116.89. Yeah. So Q is equal to h bar A delta T. Okay. So this is equal to twice of Hx A delta T. Okay. But we have to find the average heat transfer per unit area. Okay, per unit area. So take this A here, per unit area. That is watt per meter square. So this becomes in watt per meter square. So that implies Q bar by A is equal to 2 into 116.989 into delta T. Temperature difference is 60 degrees Celsius. So solve it. You will get the value of average heat transfer per unit area, which will be equal to 14028. Its exact value is 14026.86 watt per meter square, and the closest option is T. So this is it. So we have solved a similar type of question in the previous video based on the Reynolds analogy. That is option D, closest one. Okay. So the heat is lost from a 100 mm diameter steam pipe placed horizontally. That means if it is about, if the Nusselt number in ambient air at 30 degrees Celsius, this is the horizontal pipe. Okay, if the Nusselt number is 25, that means the use of characteristic length will be there. So LC is equal to D in this case. That is the diameter of this pipe. If the Nusselt number is 25 and thermal conductivity of the air is 0.03 watt per meter Kelvin, heat transfer coefficient is. Very basic question. So Nusselt number is equal to H LC by K, and Nusselt number is equal to 25. We have to find heat transfer coefficient H. LC is equal to D in this case when the pipe is horizontally laid. So LC is equal to D. D is 100 mm. That is 0.1 meter. Take care of the units. And K is 0.03 watt per meter Kelvin. So if you solve it, H will be H? H will be 75 watt per meter square Kelvin. 75 watt per meter square Kelvin. This is the answer. Okay. Next question. So the next question is for a flow over a flat plate, the hydrodynamic boundary layer thickness is 0.5 mm. So the hydrodynamic boundary layer thickness is given to you. The dynamic viscosity is 25 into 10 to the minus 6 Pascal second. Okay. And specific heat is 2 kilojoule per kilogram Kelvin. The thermal boundary layer thickness would be, nothing is given over the flow. Flow is laminar. Flow is in laminar region. Oh, the line is missing. The flow is in laminar region. Add this in the question. Laminar region. Okay. The flow is in laminar region. So the flow is in laminar region. That means I can use our relation delta by delta thermal is equal to Prandtl raised to the Prandtl number raised to the power 1 by 3. Okay. So in the previous video, we solved a question in which it was in the turbulent region. So this relation was not applicable because in that region the hydrodynamic boundary layer is approximately equal to thermal boundary layer. So find out Prandtl number. Prandtl number is mu Cp by K. Mu Cp by K. Okay. So mu is 25 into 10 to the power minus 6. 25 into 10 raised to the power minus 6. Mu Cp. Cp is 2 kilojoule per kilogram Kelvin. That is 2 into 10 raised to the power 3 joule per kilogram Kelvin upon K. Thermal conductivity. Thermal conductivity is 0.05 watt per meter Kelvin. So when you solve this, you will get Prandtl number. Oh, you get Prandtl number is equal to 1. Wow. So that means in this case, delta is equal to delta thermal, which is equal to 0.5 mm. Right. The answer is 0.5 mm. Do check the units before filling the answer. That is 0.5 mm. So the next question is, a refrigerated truck is traveling at 80 kilometers per hour on a desert highway where the air temperature is 60 degrees Celsius. So this truck is moving at 80 kilometers per hour. That is 80 into 5 by 18 meter per second. Change it here only, which will be equal to 22.22 meter per second. And the air temperature is 60 degrees Celsius. The body of the truck may be idealized as a rectangular box that is 3.2 meter wide, 2.1 meter high truck. So somewhat like this. Okay. So this is 3.2 meter wide, 3.2 meter, and this is 2.1 meter high, and this is 6.6 meter long. Great. At a surface temperature of 10 degrees Celsius. So this is Ts and this is T infinity. Okay. Assume that the heat transfer from the front and back of the truck may be neglected. So there is no heat transfer occurring through front and the back portion. Right. That the stream does not separate from the surface and that the boundary layer is turbulent over the whole surface. The boundary layer is turbulent over the whole surface. This is given in the question. So properties of air at 35 degrees Celsius are given to you. The tonnage of refrigeration needed is, the relation, Nusselt number relation is given to you. Okay. So when the air will be going over this truck surface, it will be carrying some heat from this surface of the truck. Okay. This is a case of forced convection only, and the relation of Nusselt number is given to you. Okay. So the tonnage of refrigeration needed is, the tonnage of refrigeration needed will be basically equal to the heat lost by the truck to the surroundings. Simple. Okay. So if I find out the heat lost by the truck to the surroundings, I can find out the tonnage of refrigeration needed. Okay. 1 ton is equal to 3.5 kilowatt. So Q is equal to HA delta T. Nice. Delta T is 60 minus 10. This I know. 60 is the air temperature and 10 is the surface temperature of the truck. Okay. Area by which it is losing heat. It is losing heat by this area. One surface, top surface, this side surface, and this bottom surface. 4. Okay. So the area will be twice of 2.1 into 6.6. 2.1 into 6.6 plus 6.6 into 3.2. 6.6 into 3.2. Twice, because this surface is below also, and this side surface is on the left hand side also. This right hand side surface is on the left hand side also. This surface. Okay, you got it, guys. So area is this, and now you have to find H, that is heat transfer coefficient. For that, you have been given with the relationship of Nusselt number, which is HLC by K, and that is equal to, the relation is equal to 0.036 Reynolds number raised to the power 0.8 Prandtl number raised to the power 1 by 3. You can find out Reynolds number, which is rho VL by mu. Okay, and rho is what? Rho is 1.147. V is this 22.22 meter per second. Rho VL. L is 6.6 meter, and upon mu. Okay. So you have been given with kinematic viscosity. So use this directly. That is VL by nu. Okay. So V is 22.22, L is 6.6, and nu is, not turning that page back. Nu is what is nu? 16.48 into 10 raised to the power minus 6. So that is so the Reynolds number is 8.9 into 10 raised to the power 6. Great. That means what they have given is correct. Reynolds number is coming to be greater than 5 into 10 raised to the power 5. So yeah, it's correct. And Prandtl number is mu Cp by K. Mu Cp by K. Cp, you know, Cp is 1.005 kilojoule per kilogram Kelvin. That is 1005 joule per kilogram Kelvin. Cp. K is given. Mu is what? Mu by rho is nu. So that implies mu is equal to nu rho. Nu is given to you, rho is also given to you. Use this. Prandtl number will be 0.7. 0.7. Yes, it is 0.7. Put all the value here. Put all the values here. And you will get the heat transfer coefficient as 47.6. 47.6 watt per meter square Kelvin. Okay. So put this value here, put this value here, and put this value here. Okay. LC is 6.6, K, you know, so this will be the heat transfer coefficient. Okay. So when you put this heat transfer coefficient here, it is 47.6 watt per meter square Kelvin. The heat transfer, the heat lost to the surrounding will be 166.5 kilowatt. Okay. And this is the heat which is required by the refrigerator. This is the heat which should be supplied by the refrigerator, and that implies this is the tonnage of refrigeration that is required, divided by 3.5. 166.35 166.5 divided by 3.5 will give you 47.6 tons of refrigeration. 47.6 tons of refrigeration. Okay. 47.6. Okay. Next question. Air at 20 degrees Celsius is flowing along a heated flat plate at 134 degrees Celsius at a velocity of 3 meter per second. The plate is 2 meter long and 1.5 meter wide. The heat transferred from the first 40 centimeter of the plate is this, and from both the sides. From both the sides. Okay. This. Do not forget this. Many of you will forget this line from both the sides. They'll find the heat lost from one side of the plate and they will fill that answer. Do not forget this. Okay. So this is a plate which is 2 meter long and 1.5 meter wide. 2 meter long and 1.5 meter wide. And they have asked us to find the heat transfer from the first 40 centimeter part of the plate. That is first 0.4 meters. Okay. From both the sides. So Q is equals to 2HA delta T. Okay. 2HA delta T. This I know. What will be delta T? Air is flowing at 20 degrees Celsius and the flat plate is heated at 134 degrees Celsius. So delta T will be 134 minus 20. This I know. What will be the area? What will be the area? If I have already added 2 here, do not add 2 here. Okay. Do not take twice the area. Area will be 1.5 into 4 meter square. Okay, I've already added 2 here. This 2 is for that the heat transfer is taking place from upper side as well as from the lower side. Okay, so this is 1.5 into 4. What will be H? What will be H? H you have to find out. How? H you will be finding out by using relations. And which relation can we use? Can you tell me this? For that, you will have to find whether the flow is laminar or turbulent. Let's check the Reynolds number up to this section only, because we are concerned up to this section. So Reynolds number is equal to rho Vx by mu, local Reynolds number. So rho is what? Rho is 0.998 kilogram per meter cube. This should be cube. Okay. And V is what? V is 3 meter per second. X is 0.4. And dynamic viscosity is not given. Kinematic viscosity is given. So it will be Vx by nu. Okay. This will be Vx by nu, which is 3 into 0.4 upon 20.76 into 10 to the minus 6. When you solve this, what will be the Reynolds number? The Reynolds number will be 5.78 into 10 to the power 4. Great. This is less than 5 into 10 to the power 5. That means the flow up to this section is laminar. Okay. Now this is easier for us. So for laminar flow, Nusselt number, average Nusselt number is equal to what? Average Nusselt number is Nusselt number is 0.664, and this is Reynolds number raised to the power 1 by 2, Prandtl number raised to the power 1 by 3. Because we have to find the heat transfer from the first 40 centimeter of the plate. Okay, so we'll be taking the average heat transfer coefficient up to this length. Okay, and that will be the integration of the local heat transfer coefficients from 0 to 0.4 meter by using this relation. H bar is equal to 1 by L 0 to L Hx dx. Here L will be 0.4 meter. Okay, because we have to find the heat transfer from the first 40 centimeter, that is 0.4 meter of the plate. Okay, so we will be integrating that local heat transfer coefficient here, and I'll be getting H bar. And what is the value of that H bar in terms of the local heat transfer coefficient at this length, at x is equal to L? It is what? It is H bar is twice of H, which is there. Okay. Or I can directly use this relation, which will give me directly give me the average heat transfer coefficient over this length, over this part, over this length. Okay. So H bar LC by K is equal to 0.664. Because for local heat transfer coefficient, this 0.664 is replaced by 0.332. Okay. And Nusselt number, average Nusselt number is replaced by local Nusselt number. Okay. So we need the average heat transfer coefficient over this part. So directly using this relation. So H bar LC by K 0.664. Reynolds number is 5.78 into 10 to the power 4. 5.78 into 10 to the power 4, and it's raised to the power 1 by 2. And what is Prandtl number? Prandtl number is mu Cp by K. We have not found out. Okay, you can find it out. It's simple. Mu Cp by K. Mu is given or not? Mu is not given. You can use that mu by rho is equal to mu. Okay. So I guess Prandtl number comes out to be 0.697. This is 0.697. Yes. So when you solve this, you will get H bar is equal to 10.59. 10.59 watt per meter square Kelvin. Okay. So H bar is 10.59 watt per meter square Kelvin. And when you put this value H bar here, this H bar here, the value will be the total value of heat transfer will be 1450 watt. Okay, this is 1450 watt. So this is your answer, 1450 watt. So again, a nice question it was. Always remember, when you have to find the heat transferred from a certain part, always use average heat transfer coefficient, because you cannot use local heat transfer coefficient. Local means at that point only. Okay. So average is what? Average is the integration of all the local heat transfer coefficients at this point, this point, this point, this point, this point. You get the average heat transfer coefficient. And do learn that relation, that for a laminar flow, average heat transfer coefficient over a certain length is twice of the local heat transfer coefficient at X is equal to L. Okay. Okay. So I guess this is the last question for convection, and this is again a important question. Most of the students face difficulty in these type of questions. They just see that you have to find the mass and trained between the two sections of boundary layer. They leave this question. But this type of question is very simple, very simple. Let's see how to analyze these type of questions. So air at 1 bar and temperature of 30 degrees Celsius. Air at 1 bar and temperature of 30 degrees Celsius. Mu is given. Flows at a speed of 1.2 meter per second over a flat plate. So determine the mass entrained, that is entrapped between two sections in a plate which are at a distance of 250 mm and 500 mm from the leading edge of a plate. Okay. Let us draw a diagram for better understanding. So this air flows over this flat plate and makes a boundary layer. Okay. So we have to find the mass entrapped between two sections in a plate which are at a distance of 250 mm. Let this be at a distance of 0.25 meter from the leading edge, and this section is at a distance of 0.5 meter from the leading edge. Okay, this is the leading edge. Okay, so what we have to find now? We have to find this mass entrapped between these two sections. Okay. Okay, this section, this we have to find. Great. Let me choose this. Okay. So what is mass flow rate equal to? First of all, no, this is not great color. So what is mass flow rate equal to? N dot is equal to rho A V. Okay. So can you say that if I find this boundary layer thickness delta 1, and the boundary layer thickness formed at section which is 0.5 meter away from the leading edge, that is delta 2, and integrate this velocity profile which is given from this limit to this limit. Can I get the mass entrapped? Yes, I will get the mass entrapped. This was the concept. So what you have to do, you have to find the boundary layer thickness at this section, then you have to find the boundary layer thickness at this section, and you have to integrate this equation. I'll explain it again. So let us suppose that at a very thin section dy, the mass entrapped is dm dot. Okay. So rho AV. What will be the area of this thin section in which the mass dm dot is entrapped? It will be this dy into, let that length be 1 meter that goes into the board. Okay. So area will be what? It will be rho dy into 1 into V. Okay. And this is dm dot. Okay. So now if I integrate this equation, first of all, I will put this V in terms of this velocity profile. This is V. Okay, this is V. So this is V infinity. So V becomes V infinity into 3 by 2 y by delta minus 1 by 2 y by delta whole cube, and this is okay. So put this V here. Okay, and if you integrate this between these limits, you will get the mass entrapped. It's a very simple question. Okay, so all you have to do is find the boundary layer thickness first at 0.25 meters and the boundary layer thickness formed at 0.5 meters. Do this. This will be the delta is given by, this is given by what? Delta 1 is given by 5x and root rex. Okay, some books use this relation also, 4.64x, but be aware that the relation will be given to you. Whatever the relation they want us to use, that will be given to you. Okay. So for this you need local Reynolds number at section 0.25 meters away from the leading edge. So that is Rex at x is equal to 0.25 meter is equal to rho Vx by mu. Okay. What is rho? Rho is not given, but you have been given with air at 1 bar and a temperature of 30 degrees Celsius. So can I use this? P is equal to rho RT. Yes, I can use this. P is what? P is 1 bar. Okay. And rho is that you have to find. T is what? T is 30 degrees Celsius. So what is R? R is 0.287 kilojoule per kilogram Kelvin for air. How do you know this? 8.314 divided by 28, that is molecular mass of air. So 8.314 kilojoule per kilogram Kelvin divided by 28.84. Okay, approximately. So you get rho is equal to, rho will be 1.15 kilogram per meter cube. Put this R in joule per kilogram Kelvin, not in kilojoule per kilogram Kelvin. So now you get rho. Okay. Now you have rho with you, that is 1.15, and V is 1.2 meter per second, and X, where you have to find Reynolds number, that is 0.25 meters. Okay, and mu is 0.0671. So Reynolds number, whatever be the Reynolds number, you just find this and put the value here, and you will get delta 1. I don't have the exact value of delta 1 with me. Okay, so it will be around, I guess, it will be around 0.0085. That is 8.5 mm. It will be around 8.5 mm. Okay. Now find the Reynolds number at the second section, which is Reynolds number X. Local Reynolds number X is equal to 0.5 meter. Okay, and this will be rho V 0.5 upon mu again. Again, you find Reynolds number. I don't have the exact answer with me, and put it in this equation. 5 and X will be 0.5 here in this case, and the Reynolds number, local Reynolds number Rex. The value will be around 12 mm, I guess. Yes, it will be around 12 mm. It will be around 12 mm. Okay, I don't have the exact value. So now I have delta 2 with me and delta 1 with me. Okay. So can I find out the mass entrapped within this region? Yes. Just integrate this equation. Within these limits. Okay. You have to integrate this velocity profile within these limits. That is why we have found out this, or delta 1 and delta 2. So dm 0 to m, or directly writing it as m dot. M dot is equal to rho v is v infinity 3 by 2 y by delta minus 1 by 2 y by delta cube. You integrate this is dy from delta 1 to delta 2. Okay, so integrate this from delta 1 to delta 2. So simple integration. Okay, don't get confused. This is dy, so this will be y square by 2 delta, and this will be y cube, so this will be y raised to the power 4 by 4 delta. Okay, put the limits from delta 1 to delta 2. Put the limits in meters, not in mm. Okay, you will get m dot. The value of m dot will be, this will be in kilogram per second. Okay, and the value of m dot in kilogram per second will be, okay, again the value is not given to, the final value is given that you have to fill kilogram per hour, because you have to fill the answer in kilogram per hour. So m dot is, this is around 10.96. Okay, this is not the exact value. Please be careful. This is not the exact value. Approximately 10.96. I don't have the exact data with me. It's not the exact value. Yeah, because I don't have the exact values of delta 1 and delta 2. So this will also be kilogram per hour. So basically you get the idea. I solved this question to give you an idea how to solve these type of questions. Okay, simple. The mass entrapped between these two sections is what we have to find out, and you have to find out delta 1 and delta 2 for that, because you have to integrate this equation by putting the velocity profile within these limits. You have to integrate this equation within these limits by putting the velocity profile. Take the section, smaller section dy, and you can consider the area dy into it. Okay, so it has been explained. So it's an important question, and it is not a lengthy question. Okay, so when you solve it yourself, you can get the answer within 3 or 4 minutes max, at max. Okay, please be careful with the calculation. So this was all from convection, and the next chapter we'll be solving will be, I guess, it will be radiation. So this was all from convection. Thanks.